Welcome back to all of you. Uh, we have been discussing the bonding theories of transition metal complexes, and right away, let me share the screen. We will start from the point where we stopped in the last video. So, all right. So, in the last video, we briefly discussed the assumptions of the crystal field theory, and then we learned that how when the ligands are approaching uh, the d orbitals for the metal ions, okay, first there is a electrostatic attraction because of which the energy of the system get stabilized. The system gets stabilized by reducing energy, and then when the ligands are coming little more closer, a symmetric field will be generated around the metal ion. Okay. However, when these ligands are coming even more closer, so a octahedral field will be uh, created in that case. If you are discussing the octahedral geometry, and once the octahedral field is created by the ligand, then we know that the dz square orbital and dx square minus y square orbital, they are facing the ligands directly. So their energy goes like plus 0.6 delta O higher and then the barycenter, and the energy of the rest of the orbitals, that is dxy, dxz, and dyz. Let me do it. Dxz, dyz, and dxy, energy of these three orbitals, it goes minus zero point 0.4 delta O below the barycenter. All right. So this difference between the energy level of this T2G, that is this level, and the energy level this EG. So the gap between T2G and EG, that is called delta O. Right. So this delta O is in case of when we are discussing the tetrahedral symmetry, tetrahedral geometry, because the number of ligand is only four, and in this case, orbital none of the orbital is directly approaching any of the ligand, right? So ligand and orbitals are not in the same axis. Okay, however, the T2G set is more closer, okay, at an angle of 35.16, and E set, basically the dx square minus y square and the z square orbital, they are at an angle of 54.44, right? So the dx square minus y square and dz square orbital, they are slightly away compared to the other three orbitals. So in this case, it's the reverse of what we have seen in case of octahedral, and it will be just the reverse of the splitting will be just the reverse of that. Okay. E, that is dx square minus y square and dz square orbitals will have lower energy while the other three orbitals will have higher energy, right? In this case, the G, that is the Girardi, that because of the centrosymmetry, that term was used in case of octahedral, that is not being used over here. It is just the E and T2. The gap between E and T2 is delta T, that is the crystal field splitting in case of a tetrahedral geometry. So this I told you in the last video also that delta T is less than delta O, and the reason for that, this relation is given over here. Delta T is equal to 4 by 9 of delta O. So the reason is that there are only four ligands instead of six in case of tetrahedral, and none of the orbital is facing the ligands directly. Okay, so both the factors roughly contribute by 2 by 3 into 2 by 3, so a 4 by 9 factor comes in. Okay, I told you that is basically supported by the experimental data that we will see in a short while. And I told you that all the tetrahedral complexes, because of this gap between T2G, T2 and E orbital is very small, all of them are likely to be high speed. Okay. Now, so this is how you can depict in this case that a octahedral geometry on this left hand side and a tetrahedral geometry on the right hand side, and you can see the gap between the E and T2 is smaller compared to a gap between the EG and T2G. All right. The dx square minus y square and dg square are lower in energy in case of tetrahedral, while in case of octahedral, they are of high energy. Okay. Reason I told you that In octahedral geometry, they are facing the ligands directly, while in case of the tetrahedral, they are away from the direction of the approach of the ligands. Okay, so that is the reason. That is how you can basically understand this, the splitting of the tetrahedral and octahedral geometry. Okay. Well, you can also have a look at the d orbital splitting in square planar field, ligand field basically. Okay, so nickel, palladium, platinum, and sometimes copper and gold and silver complexes are square planars. Okay, and when they are square planar, you can understand them that it is, let's say there is a octahedral geometry, right? So 5d orbitals will be splitting just like I just explained to you. The two orbitals goes higher in energy and the other three orbitals comes lower in energy. So here, in this case, you can think of that the dx square minus y square orbital has four lobes. Okay, sorry, this is just the wrong thing on the slide. This has the four lobes, so it will be repelled by the four ligands, while dz square orbital will be repelled majorly by two ligands coming along the z direction. Okay, dx square minus y square will be repelled by four ligand coming along with the plus x minus x plus y minus y in that direction. Okay, so because of that, now when the ligand field will be, when the ligand field will be starting to increase, okay, this repulsion will be more. Okay, and there will be a time that these two orbitals will be no more would like to be in the degenerate phase. Okay, because the they are facing more and basically different amount of repulsion from the ligands. So it will be turning like this. Okay, the three T2G orbitals are over here. The dz square, we are discussing a particular case D8 system because mostly the square planar geometry is observed in case of the D8 system, right? Nickel to platinum to uh, all are having the D8 electronic configuration. Most of their complexes exhibit a square planar geometry. Okay, so D8 system, as I told you, that degeneracy will be removed and it will be situation will be like this. Okay, first, and then when the both the electrons are in the dz square orbital, so you know the dz square orbital shape. I hope you remember. Okay, it has two lobes along the z-axis. So if the z orbital is having dz square orbital is having two electrons, forming bonds along this direction will be resulting into a lot of repulsion from the dz square electrons and the electrons present on the ligands, right? So what will happen that the two bonds along the z direction will not be formed, right? So you can think of that there is octahedral geometry and two bonds from the octahedral are removed. So the resulting geometry is a square planar geometry. It's a good way of understanding it. Okay. So although it's not like first octahedral will form and then two bonds will be removed. Not, it's not actually like that. It is just the way. It's a good way to explain it that square planar geometry is resulting like if the two bonds along the z directions are removed, that is how it looks like. And in this way also, from the orbital splitting diagram point of view also, it looks quite convincing to understand this phenomenon in this way. Okay, so the resulting, you can say the resulting geometry will be resulting splitting of the orbitals will be looking like this, and the dxz and dyz, okay, they will be stabilized maximum, then dxy, then dz square, then dx square minus y square. All right, this is how you can explain that a square planar geometry is formed as per the crystal field theory. Okay. All right. So then, okay, the similar thing is again explained here that this is octahedral. Okay, imagine that this is the octahedral. Okay, and this is tetrahedral, and you see this is another four coordinate geometry. So in the different geometries, right, this is how the different splitting diagrams looks like. So a square planar, you can see the dx square minus y square now, because all the four ligands in this case now, okay, they are affecting the dx square minus y square orbital. You see directly facing all the four ligands. So obviously the energy of this orbital will be very high, and the next all the four ligands, although not directly affecting xy dxy orbital, but it is close. They are at just at a 45-degree angle because they are in between the axis, right? So the next orbital which is being affected most in the square planar geometry is the dxy orbital. Okay. After that, you see the dz square orbital because now none of the ligand is affecting dz square, so it is coming down even below the barycenter, and dz square is now below with the dxy. Okay, dyz and dxz, they are in between the axis and they are not getting affected. So they are farthest away from the approach, and so their energy is the least in this case, square planar geometry. Right. So now all the three geometry that we have understood is octahedral, where the T2G and EG sets are being formed. Then we have a tetrahedral, and we have tetrahedral in which the E and T2 sets are being formed. Here it is delta O, the gap is delta O, here it is delta T, and here the gap between the lowest energy and the highest energy, that is basically the delta SP, that is the square planar difference in the or the crystal field splitting in the square planar geometry, right? And delta SP is said to be like 1.84 times of delta O. You can see it is even higher than the delta O, because as I told you that the geometry, square planar geometry, is generally forms with a strong field ligands. So when there are strong field ligands, obviously there will be much more repulsion, so the splitting has to be more. Okay. Now I hope that you have understood that this direction of the approach of the ligands, how they are approaching the metal ion, that is very important to understand the splitting, how the d orbital splitting is taking place. For example, I can discuss more examples. See trigonal bipyramidal geometry. Okay, you know the trigonal bipyramidal geometry, right? There are three ligands in the equatorial position, each at a 120-degree angle, right? And then there are two ligands along the z direction, right? As you can see that along the z direction, there are two ligands. So this is obvious that if the two ligands are directly affecting dz square orbital, so energy of the dz square is obviously is going to be highest. Okay, now in this case, since the three ligands are at 120-degree angle, right? So you know that they are not along the axis, right? They are in between the axis, right? So when they are in between the axis, dxy orbital is also in between the axis, in the xy plane. So dxy and dx square minus y square are having the equal distance from the direction of the approach of the ligands. So obviously their energy will be equal, and a new energy level will be formed. The dxz and dyz having the z component and of course the x and y component, okay, their energy will be lowest because they are mean the farthest away from the direction of the approach of ligands. This is how basically you can understand. So in order to actually, if you even if you do not remember how the splitting diagram should look like, you can still make energy level diagram or d orbital splitting energy diagram just by imagining how a geometry looks like and how the shape of the 5d orbitals look like. If you correlate the two, the shape of the geometry of the complex, right, and the shape of the 5d orbitals, right? You know the dz square orbital is just like in the z direction, just like this. So they're directly two ligands are directly affecting it. Energy has to be high. So comparatively, you can see that other orbitals are not facing the ligands in the same way, right? So their geometry, their energy is going to be, of course, lower. Another example I can give you is a pentagonal bipyramidal geometry. Again, there are two ligands in the z direction. Okay, just try to imagine a pentagonal bipyramidal geometry. In trigonal bipyramidal, you had three ligands in the equatorial position, and now in the pentagonal bipyramidal, you have five ligands in the xy plane. So dz square again it will be highest because this is facing the ligands directly. So dz square is highest, you can see. All right. Dxy and dx square minus y square Compared to a trigonal bipyramidal, you can see which is almost in between the two. The energy of the dxy and dx square and square is almost in between, right? Close to very center, like the energy almost not affected, right? Higher. However, if you look over here, they are also higher in energy. dxy and dx square minus y square. Why? Because now they are now in the close vicinity of five ligands instead of three in the trigonal bipyramidal. It is pentagonal bipyramidal. There are five ligands in the equatorial that xy plane. So five ligands are affecting the energy of dxy and dx square minus y square. Obviously, more repulsion, so they will be higher in energy, right? So not only the splitting of the orbitals, but also the level of the energy, whether high or low. That also you can understand just by looking at the geometry and the number of ligands. Okay, related energy diagrams can easily be created. All right, the extra divided again because they are not again they are farthest away from the approach of the ligands, and so their energy will be lowest in case of pentagonal bipyramidal also. I hope that you are able to understand the relation between like the geometry and the splitting diagram. That is very very important for the crystal field theory point of view. This is a summary of the deorbital splitting in most of the important geometry that we will come across. I started with the describing octahedral geometry, coordination number 6. Okay, this is in terms of the DQ, okay, the 10 DQ. So I was saying 0.6 delta O, 0.6 delta O is equal to 6 DQ. So dz square dx square minus y square is 6 dq, and dxy dxz divided is minus 4 minus 4 minus 4. If you make a diagram of the crystal of the d orbital splitting, you have the y-axis. Okay, in between you put the zero, and then you put plus one, plus two, plus three, and you put below zero minus one, minus two, minus three, like that. Okay, and you can easily make the energy level diagram. Let's say the put the two d orbitals dz square and dx square minus y square at 6 dq, and the other three at minus 4 dq. In case of tetrahedral, you can see this is minus 2.67, minus 2.67, and plus 1.78, 1.78, 1.78. All right. If you see the gap, this is 6 and minus 4, so total is 10. Here it is minus 2.67 minus 1.78. So this is if you add them, so this will be like 3 and around like 4 point something, right? This will be 4 point something. So compared to 10, it is around 4. So you know that it is basically like 4 by 9. What I told you, the relation between tetrahedral and octahedral, okay, 4 by 9. So if you just add them together, you see the gap. That is how it's going to be. So it's no surprise that you will see if delta t is equal to 4 by 9 of delta O, the relation you will see experimentally also. No surprise. In case of a square planar, I told you that this poor dx square minus y square ligand is facing all the four ligands directly along the axis. So you see the energy of this orbital is 12.28 positive, very very high. Next is dxy 2.28, slightly above the barycenter. All are in negative, rest of the all are in negative. Minus 4.28 is dz square. So see, this is slightly above the barycenter, and this dz square is slightly below the barycenter, slightly quite below, minus 4.28. And then you have dxz divided, even lower in energy, minus 5.14, minus 5.1. Okay. See, so this energy, this is the exact picture. If you have this table, you can make an accurate d orbital splitting diagram for any of the geometry. Look at the cubic field. Cubic field is very similar to octahedral field in terms of the approach of the ligands. Okay, in the cubic field, we know that every corner of the cube is having a ligand, right? So you know accordingly the dz square and dx square minus square, again they will be closer to the approach of the ligand, so they will be away from the approach, okay, because they are along the axis, and ligands are not now ligands are coming now from the in between the faces of the tube, and metal d orbitals are along the axis, right? And ligands are not coming from the faces; they are not coming along the axis; they are coming from the corners. So dz square dx square minus y square will be minus 5.34 minus 5.34. However, the in between the axis they will be facing ligands closely now. So 3.56, 3.56. Okay, the total gap is close to 9 because 5 plus 3 8, and this is 8.9 basically. That is the total gap compared to a octahedral that is 10 dq. This is total gap is like around 9 dq. Icosahedral 0 0 0 0, right? You're surprised because there are 12 ligands here. Coordinate number is 12. And how come? You will be expecting much more splitting. That's what you were telling in case of octahedral. There are 6 ligands, but tetrahedral only 4 ligands, less splitting. Here there are double two octahedral. Then why 0 0 0? Okay, you remember that the symmetric field. When there are 12 ligands, they'll be surrounding all the 5d orbitals, very like just like a spheric field, spheric symmetrical field, right? So wherever you put the orbitals, they are going to face the ligands almost from the same angle because ligands are everywhere. 12 ligands are there, right? So although the energy of the d orbitals will be going very high, but there will be no splitting effectively. Okay, so this splitting will be just basically the gap of the where something is stabilized, something get destabilized. But here everything is getting destabilized, right? Energy of the all the d orbitals is going high, so there is no splitting. So please understand this splitting. Splitting will be taking place only when the direction of the approach of ligand is such that they are affecting out of the 5d orbitals, okay, some ligands more, some ligand less. Then only splitting will take place. Otherwise, splitting will not take place. That is what we learn in case of icosahedral. Given given this all these figures to you, okay, if you know these figures, you can make any of the energy level diagram. For example, you see over here, as I was just telling you that you take y-axis and you have like 0, right? And this is in terms of again delta O. So 0 0.1, 0 0.2, 0 0.3, 0 0.4, all the way up to 1.2, because that 12 dq or 1.2 we need for the square planar geometry, that is the dx square minus y square is occupying that much higher in energy, right? dxy you can see in case of square planar above the barycenter. This 0 is defined as the barycenter, and this is true for all the geometry irrespective of whatever the geometry. This barycenter will hold true for all the geometries. Okay, you can make it the y-axis in the negative direction also, minus 0.1 to all the way minus 0.7, and you see that these dxz and dyz are generally they are the lowest in energy because ligands in most of the geometry we are not affecting them much, except in case of some geometry like uh, tetrahedral is one of them, not shown over here, and diagonal bipyramidal again you can see that these orbitals are higher in energy. Okay, because dxz and dyz they are in between the axis, and the ligands are also approaching almost in between the axis. So all of them, although dxy and dx square minus y square is slightly more closer to the approach of the ligands, so the energy in case of trigonal bipyramidal, energy of these two orbitals will be slightly higher than the other two. Okay, however, all four are below the barycenter. Okay, so please try to correlate the geometry with the d orbital splitting. Just we don't have to just mug up like just you don't have to the rote learning that this is where the splitting looks like. Try to imagine what is the geometry. Try to imagine the shape of the 5d orbitals, and I am sure that you will be come up with after this explanation. If you seriously go through, you will be able to make your own diagrams correctly. Okay, always remember this table. Okay, as I told you, and if you just see that, if you just see that uh, uh, in terms of the exact numbers of like 10 dq, all the data is over here. Before that, what I'm explaining to you, this diagram is qualitative, this diagram is also qualitative, but all these things are in quantitative information over here. This particular table I have taken from the book of James C. Huey, right? There are more geometries are given there, and yes, this is the picture from the Huey book is given over here. And not only just the all the major geometries that is most common for many transition metal complexes, but even the less common ones are also given over here, like linear, just the trigonal or the prismatic. Okay, all geometries are given over here. Their data is over here. Okay, and from here only I just made this some of the selected ones so that you get this more clearly what exactly this data is. Okay, so I hope I was able to make you clear that what are the assumptions of the crystal field theory. Then d-orbital splitting, which is octahedral, tetrahedral, square planar, trigonal bipyramidal, square pyramidal, square bipyramidal, right, and relative splitting. This is a very important as far as the crystal field theory is concerned. You need to understand, especially at the that graduation level or master's level, you need to understand most of the geometry, just not octahedral and tetrahedral. So, okay, so all the geometry you please try to draw practice for drawing the orbitals. Also try to practice their splitting diagrams, and if you do that, I'm sure you will get a very good understanding of the crystal field theory and the data that we are going to see in shown in the other videos. So with that, I would like to also make it clear to you that now with this knowledge of d orbital splitting, that we are going to now understand a little bit more in details, and based on that we are going to explain the property of transition metal complexes. Okay, so for example, you will see the extent of crystal field splitting, why in some cases this is high, why in cases it is low, so factors affecting the extent of crystal field splitting, right. You will also see the spectrochemical series in the same discussion. Okay, spectrochemical series is a very powerful information to understand a lot of properties of transition metal complexes. Then you will see how this data can explain us the stability of transition metal complexes, and we will do the crystal field stabilization energy calculations. Okay, CFSE calculations, very popular as far as the this chapter is concerned, and from the many competitive exam point of view, calculation of CFSE, okay, is very important. Distorted geometry, we will see how crystal field theory is able to explain the distortions in various geometry, which other the previous theory like Valence Bond theory or Werner's theory were not able to explain. You will see how we can predict the structures of the spinels, the oxides, metal oxides, okay, and the other trends and properties of metal complexes. Okay, finally, we'll see if there is still some limits of the crystal field theory, what still the crystal field theory also is not able to explain. Okay, so this is the next course of action that we are going to do now. All right. So with that, now let me take you first to the illustration of CFSC, that is again the crystal field splitting energy. Please don't get confused. The CFSC term is generally confusing sometimes. That one is crystal field stabilization energy and one is crystal field splitting energy. So here I am talking about the crystal field splitting, which is the gap between, like say in octahedral geometry, the gap between T2G and DG. While the crystal field stabilization energy is different, that is the overall qualitative overall stabilization if the crystal field was not created. Okay, that we will see later. So, for example, here, if you would like to see that how much is the splitting in a particular geometry like octahedral or tetrahedral, so how do we do that? How do you find out what is the gap? So for that, you need to do an experiment, okay, using a equipment called spectrophotometer, or to be more specific, UV visible spectrophotometer you need, and you need to record a UV visible spectrum of any metal complex. For example, we have taken here titanium hexaco 3 plus complex, right? And it's a D1 complex, and the electron occupies in the lowest energy orbital. So it's octahedral, so it has to be the T2G set, right? One of the three degenerate T2G set, DXY, DXZ, DYZ. Electron can be in any one of them. On the single electron, it's a D1 system. It has a purple color. So if you would like to, now since we know that d orbital splitting is taking place, so you can easily say that it is the configuration is T2G1 EG0, and if you provide the light energy to this system, okay, the system will absorb energy in order to excite the electron from T2G level to the EG level. So the resulting configuration will be T2G0 EG1, right? So this is where the energy will be absorbed in order to excite electron from T2G level to EG level, because it's octahedral geometry, right? If you just record the spectra, in the spectra you know that at what energy this excitation is taking place. Okay, so you can see this is a broad spectra although, but the maxima is to 20,300 centimeter inverse, or basically somewhere around 500, 510 or 520 nanometer. Okay, so in the nanometer it is around 500 nanometer, and in case of centimeter inverse, this axis, this scale, which is 20,300 centimeters, okay, which corresponds to about 243 kilojoules per mole. Okay, there are other conversion factors are given over here. A 1000 centimeter inverse is generally 11.96 kilojoules per mole, or 2.86 kilocal per mole, or 0.124 electron volt. So now, from this recording, this spectrophotometer, which there is a separate video that I can share with you. It's also available, that how a spectrophotometer works. So basically, I can tell you that in a spectrophotometer, which you will be using in your practical lab, you can take a complex, make a solution of it. The solution of the, let's say, if you take titanium hexaco 3 plus, it will look like purple in color, and you take in a glass, that it is called cuvette, glass cuvette. You take the solution. That cuvette, you will take it this to instrument called spectrophotometer, and in the spectrophotometer there is nothing but there is a light source, right, which will provide you all this light ranging from, let's say, 333 nanometer to 1000 nanometer, or 10,000 centimeter inverse to 30,000 centimeter inverse. Sometimes even more depending on the length, right? Generally from 200 to 1000 nanometer, that is in the UV visible range. That is the length generally that is provided. So those lamps will be giving energy. Then you have the cuvette. So you need a sample holder. So you can put your sample somewhere in between there. And after that, light will pass through it. So you need to see how much light you have given and how much light finally came out. So you know how much light is absorbed in the process. And from there, the spectra, you know that this is the light absorbed. So you know that uh, this is the energy basically corresponding to the gap of the T2G and EG. So you know your crystal field splitting energy also in this case. Sometimes the spectra is not that simple. It can have multiple bands, and that can be explained by considering the spectra, the spectroscopic states, and also the distortions, and how many energy levels are resulting within this system. That will describe that how many bands will appear. That is something that we will discuss after that we discuss the stability constant, and then we will be coming to the spectra. Okay, that is also part of this coordination chemistry course. So just please wait for that. All right, so I hope I was able to make you clear over here in this slide that there is a UV visible spectrophotometer, the instrument that is being used in order to find out where a particular metal complex is absorbing, and that absorbance of the light can be correlated with the d-orbital splitting, right? The d-orbital splitting, like we have seen, this, like this gap between the That's the octahedral geometry. This is the T2G level, this is the EG level. When you excite electron from this level to this level, okay, as you know that electrons will not be absorbing energy lower than this, right? Because of the that the energy has to come in the form of quantum. So it will not be just going in between somewhere. It will be taking the energy which is equal to this gap. All right. So now you see again that gap is corresponding to the this energy which is being absorbed by the metal complex. All right. So now you know the gap. So what you can do, you can basically make a large number of metal complexes, right? And record the UV visible spectra. And if you record the UV visible spectra of many complexes, you will be having an idea that with this metal and this ligand you get higher crystal field splitting, or with this ligand you get a lower crystal field splitting, right? So based on that, if you see, you can get an study, you can do a study of nature of the ligands, right? Which ligand is causing more splitting, which ligand is causing less splitting, and based on that, you can make a series. Some ligands which are causing less small splitting or weak field ligands. So say crystal field splitting in the range of 7,000 to 30,000. Okay. And those which cause more than 30,000 generally. Okay. Sometimes we just say the ligands which can cause low spin nature complexes, they are strong, but this is either way you are fine, either way you can understand this is a relative phenomena. Like for example, the iodide, bromide, sulfide, they are weak field ligands because they do not cause much splitting of the d orbitals. However, if you see, and ethylene diamine, ammonia, bipyridine, they are quite strong actually compared to these iodide, bromide, or azide, or urea. Okay, so they are on the right hand side of the ligand. And finally, if you see cyanide, carbon monoxide, they cause maximum splitting with any of the given metal ion. Okay, so they are the strongest ligand, right? So how do we know this information? Again, I am repeating, this information is coming from the experimental data, the spectroscopical data. That's why this is called spectrochemical series, right? This is called a spectrochemical series because this data which are used to create this series is coming from the experimental data from the spectrophotometry. Okay, so now you can easily predict that if you want to make a complex with a weak field ligand, there will be a smaller splitting. If there is you want to make a ligand with higher splitting, you can choose a ligand from the right hand side of the the periodic, sorry, this spectrochemical series: ammonia, ethylene diamine, bipyridine, phenanthroline. Okay, all the ligands, cyanide, carbon monoxide, they are strong field ligands. Okay. As you know, the color, as I told you, I was explaining that is a purple. Titanium hexaco is a purple color. This can be easily explained because it is absorbing the energy around 520 nanometer. So the corresponding color, okay, the one which is absorbed, corresponding the color, I'm sure that you have studied the color wheel. You will see if you see the color wheel, you can clearly tell that because it is absorbing certain light of this wavelength, the resulting color will be that wavelength. Resulting color will be that. All right, the corresponding color to whatever light being absorbed, complementary color will be you will be seeing. Okay, so you can explain the color now very easily. You can explain some other property why some ligands are weak field ligands, why may not be why they are weak field ligands, but you know the nature of the ligands, that these ligands are weak field in nature and these ligands are strong field ligands. Okay, this is a great information that you obtained from the crystal field theory, and if you know that if you relate them with your metal complexes, this can serve with a lot of information and to explain the various properties of transition metal complexes. Okay, with that information, maybe I'll close this particular video over here, and in the next video we will take some data, the real crystal field splitting data, and we will see that other factors like oxidation state. We have seen the factor of the ligands, the ligand field, right? Some ligands are causing more splitting, some ligands are causing less splitting, weak field or strong field ligands, and we will see some other factors, whether it is the oxidation state or the nature of the metal ion, whether it belongs to 3D, 4D, or 5D series, and based on that, we will be trying to explain the experimental data of crystal field splitting. All right. So, uh, thank you very much. I'll see you in the next video.